Log on, tune in, find out. Another good idea from Cambridge.
So, welcome to all to the weekly seminar that's starting today. That will be held every week at the same time. And so we'll have people who are visitors to the program. And our very first speaker is Pauline Lafitte from the Université de Lille. We'll speak about numerical explorations of a forward-backward diffusion equation.
Okay. At first, I'd like to thank José Antonio for inviting me to the Newton Institute in this program. I'm having a very good time, so thank you very much. And also, I'd like to thank the organizers of the seminar for allowing me to talk about this new subject for me, actually. So this is joint work with Corrado Mascia from the University of La Sapienza in Rome. And actually, we're interested in phase transition model for polymers. Actually, we are exactly interested in the glass transition point, meaning that at some point the polymers form some kind of glass, and you have two viscous, it's assimilated, sorry, two viscous phases. And we are actually interested in seeing how these transitions move. So the main interest actually was to numerically approach the transition and see how it develops. So this model was actually proposed by Jekyll and Frisch in 1985, and it takes this form, the form of actually a second order derivative in x and one derivative in time. And so the U is the mass, and V is some kind of potential which is actually defined like a certain diffusion function f of u plus a convolution of a memory term. So it's a convolution in time of a memory term, theta, and another function psi and phi with a derivative. Okay, so the function we have in mind for phi is this cubic shaped function. So actually the cubic shaped yeah, thanks. So actually the cubic linear shaped, the cubic shape, sorry, is very complicated to take a grasp of. So what I will be presenting is actually this piecewise linear shaped diffusion function. So the thing is that the first model was presented with this memory function theta, and actually what we can take for theta is something which decreases exponentially from 1 to 0, so it's really a memory in time and local in space. So what you get choosing psi with this form, so linear, and depending on the relaxation time tau, you get this third order equation. And actually it was the analysis was performed by Novicohen and Pego in 1991 in the case of no memory, meaning you make this term disappear and keeping this epsilon term. So if you remember the shape of phi, so maybe I'll just draw it quickly. So here you have u and phi, and so this cubic-like function, meaning that we're really interested in the 3 zeros here, meaning that we have here, so it's non-monotone, of course, and we have a kind of forbidden area here, of course, since the diffusion here is, well, the diffusion equation, if you get rid of epsilon here, the diffusion equation, of course, is ill-posed in this region. So let me just note the points of interest. So here is B, here is A. And we'll make use of these points too. This is D, and this is C. So, of course, when you consider the equation without epsilon, as I said, the problem looks like it's ill-posed. The thing is that with epsilon, you can show that there is global existence and uniqueness of the C1 solution. There's no problem with this one. So what we are really interested in is the actually limit epsilon goes to 0. So we don't know how to exchange the limits tau to 0 and epsilon to 0. The limit we're interested in is tau is already 0 and epsilon is going to 0.
Excuse me, what is U physically? Like it means the point.
It's the mass, actually.
And tau is going to negative, so to speak. So we just
Actually, well, it's a mass with respect to some. Actually, we choose here to have kind of symmetry around some zero. So yes, it's just renormalized, let's say. Okay, so the case with no memory is really this one we're interested in. Okay, so here with the ill-posedness, it means that we will divide the X space, the U space into 3 phases. This one, S1 and S plus, are really stable phases, since the diffusion is well defined and is positive in these phases. And here is the unstable phase, where the solution cannot be. So, for epsilon going to 0, actually, if you linearize the problem around a state which is in U, what you really see is that the solution escapes exponentially fast in time to one of the two stable phases. So, the first description that was given of this two-phase solution was by Plotnikov. So it's a series of work in the 90s, and actually he described the solution as being a convex combination of 3 phases. Actually, there were parts in the 3 phases. But the thing is that he lacked a result of uniqueness. What he showed, however, was that in the distribution sense, there was some inequality that was verified. And this inequality actually looks like an entropy flux pair thing, which arises in conservation laws. So, actually, the idea is that when you start with a 2-phase initial condition, meaning that here, here is the xt plane. So if you start in S minus on the left and S plus on the right, you have, well, kind of 3 cases that can occur. Either the transition doesn't move, the interface doesn't move, or it moves to the right, or it moves to the left. Okay. So here is what, from now on I'll denote gamma is the interface, and the psi of t is the function actually of the time that describes. So the first concept, concept of solution, of weak solution, was introduced by Evans and Portiliero in 2004, making use of this analogy with conservation laws, meaning that they were considering piecewise smooth solutions and using this entropy inequality. So at the interface gamma, what happens is that you have, of course, transmission conditions, meaning that phi must actually coincide on the transition gamma, and also you have some kind of condition, some kind of jump condition for the derivative of phi of u. It is linked actually to the derivative of the well, actually with the speed of the transition of the interface. Also, what they showed was that there were entropy conditions, meaning that if you arrive at these points, these most important points, A and B, it means that the interface will move. What I mean is that if you are within the stability region for phi, meaning the values or the limiting values are within A and B, then the interface will not move. It's a fixed boundary. If, on the contrary, you reach the point A, the interface will move to the right, otherwise it will move to the left. I will actually show you some pictures afterwards. The local existence and uniqueness for this concept of weak solution was showed by Masha Terracina and Tesei in 2009. Okay, so what we said was if T, so T will denote the value of phi of u, psi of T and T. So this value T must be within A and B. That's what the entropy condition told us. So there are three cases. If T is strictly within A and B, then the transition is, the interface is steady. It doesn't move, like in this case. So what does it mean in the u phi of u plane? Actually, it means that if you start, so here is the initial condition. You have, so here it's for a Riemann problem, for example. So you have something like this initially. So this is x and this is u. And you have, so this is u minus and this is u plus. So with some condition, you can say that if u minus and u plus satisfy are such that f of u plus plus f of u minus is within AB, then what happens is that they tend to balance at some balance point of phi of u at each point, meaning that the solution will look like this after some time. So right. So this is in the x u plane, meaning that if you look at phi of u, they will connect. And they will connect at precisely this value of phi of u. So the second case, if t is equal to a, then the interface moves to the right. What does it mean? It means that actually if you start from too far in the left-hand plane, in the left-hand face, sorry, then you will go to the limiting state. Here it's this point C on the left and this point A on the right. And actually arriving in this, which is, you see it's at the border of the let's say, admissible u phi of u region, then it makes the interface move to the right. The third case is, of course, if t is equal to b, then you have the converse, meaning that the solution will go down on the right hand side and go up on the left hand side, but will balance at this point, meaning that the interface will move. So it will look like this. This I forgot. Yes, here maybe. So it moved to the left. So it means that having a look at it will look like this. So here is what you can get if your initial data is, for example, strongly oscillating or something like that. So the problem we were actually interested in at first was to solve the Riemann problem, because we needed some test case solution to validate the numerical schemes. So the Riemann problem, that so this kind of initial condition, actually can be explicitly solved, because actually there are self-similar solutions that you can identify by doing this scaling, which is an invariant scaling. So it means that actually for the Riemann problem, the solution has an interface that is that has this shape. Okay, meaning that it's either parabolic or square root. It depends on the point of view. So the discontinuity curve actually is completely defined by this value zeta bar, and you can find f by solving this equation, this second order differential equation. Of course, you have to remember that phi is of course strongly nonlinear. The problem we considered was the symmetric case. I will actually explain how to go to other cases. So the symmetric case, it means that phi is exactly as I showed you, but here we actually take something like this. Here the values are 1, minus 1, 1, minus 1. So here it's 2, and minus 2. Just to make things really explicit. So B is minus 1 here, and A is 1. M is 2, and Q is 3. So what you introduce now is the error function. So you see that, well, of course, what we are doing is solving a linear diffusion equation in half spaces, and doing some connection between the two solutions at some point. So it seems natural to introduce these error functions, since, well, it really should look like this. And what we find is that actually you can express completely u as a function of x over square root of t, as I showed you before, and it's actually a combination of these error functions, and you have to consider also here phi plus and phi minus are the continuation of these two linear functions. So this is phi minus, and this is phi plus. Okay. So the characteristic condition, that I told you about to know whether the interface will be moving or not is exactly this one in the symmetric simple case. Otherwise, you have some combination here of m plus and n minus, meaning the slopes of phi on the stable and on the left hand and right hand stable regions. So here it looks kind of nice with A and B being -1 and 1. You just have to check that this value is within -1 and 1. So if it's within -1 and 1, the interface is steady. It won't move, meaning that, as I showed you on these pictures, the solution U will look exactly like this, meaning in steady interface. The solution of the heat equation here, and a jump, okay? And for phi of u, actually, solves the diffusion equation exactly like this. And it's continuous. The only thing is that at that point, the regularity is not clear, of course, since you have to connect the two solutions. Okay. So here it's in the xt plane. What you can see is that well, you kind of see, I don't know if it's really nice, but you can see the parabolic shape actually of the self-similar solution. And you see that, of course, here there is an interface, and for phi there's no interface. Okay, now if the condition is false, then the interface is moving. So theta bar is given by a very nasty implicit relation. Because if you remember, G is this very nice thing here, which is kind of not explicit at all. But well, with Newton logarithm, you can find zeta bar. That's not a problem, actually. So here in this specific case, minus 2.1, 4.2, you see that if you sum up the two values, f of u plus f of u minus, then you are not in the good case. You are in the case which is here the first case, meaning the interface will move to the left. And so this is what the solution looks like afterwards. So here it's pretty clear. Well, the shape of the interface is pretty clear. It's parabolic. Okay, so the scheme we introduced actually is based on a very simple centered discretization for the second order term in X. So we consider at first the semi-discrete scheme, just a discretization in space. And so the initial condition is the initial condition corresponding to the Riemann problem, meaning u minus and then u plus. And what we take is Neumann boundary conditions, meaning the derivative should be 0 at left and right, at the left and right boundary of the domain. So I just quote for the record the matrix, because I'll have to explain something about it afterwards. So the semi-discrete scheme is very simple, in fact. You just have, so this is a semi-discrete scheme for epsilon strictly, well, epsilon positive, okay? Meaning that you have here to invert a certain matrix, and here you recognize the discretization of the second order term in X. The thing is that this matrix is invertible, of course, since A is semi-positive definite. So, okay, it's a very nice problem. Epsilon can be taken to be 0 since it's invertible. We have no problem with that. So that's the case I will show you. So remember that, of course, phi is mostly linear, so we can hope, well, to do something with this problem. Problem is, of course, when you have to face the interface. So you can actually think of this problem, this semi-discrete problem, as a non-autonomous problem, meaning that here you can write it as minus m of tau u tau plus w tau, where m of tau and u and w tau are actually well, a matrix and a vector which are piecewise constant. Of course, they change as soon as one of the components changes phases. Since, okay, when it changes phases, the discretization is not the same. So here I'm going to talk only about the special symmetric case m equal 2, q equals 3, which is actually this one. The slope here is 2, the slope is 2, and actually the slope is minus 1 here. So it's a very simple case. The only thing is that you can generalize very easily the things I will show you just by doing a matrix product with a diagonal matrix, actually. Because the slopes here and here are really, well, you can see them very easily in the semi-discrete scheme. Okay, so in the case of a steady interface, meaning that u plus plus u minus is within minus 1 and 1, then you can have a look at the differential, the system of ODEs, which is dv over d tau is minus 2 A being still this discretization matrix, okay, the Laplacian. Thing is that what you can show is that the exponential of minus 2A is actually has positive, has, well, non-negative terms, actually positive, but it's not really important. The thing is that with this result and the fact that the infinite norm is less than 1, then it means that the structure, the two-phase structure of the discretized solution is preserved. Since you have, writing the solution is, of course, the solution is simply exponential minus 2 tau A V of 0. And see if, V of 0 is between minus 1 and 1, then with the exponential it won't change anything. And so the structure is completely preserved and the interface will not move. So this is for the, let's say, L-infinity analysis of this, semi-discrete scheme. With the L2 analysis, what you show is that you have an asymptotic state, which is exactly phi of u plus phi of u minus over 2, which is, if you remember, exactly the characteristic condition I was talking about to know whether the interface will be moving or not. And then you get the end states by taking just the inverse of these phi minus and phi plus functions. So this gives, well, good results. The thing is that since you know in advance that the interface will not be moving, you can use an implicit scheme, a fully implicit scheme, if you want to discretize everything. Since, of course, well, you won't have any CFL. It will be much more efficient, let's say. And the thing is that you can try also fully explicit. But the thing is that, well, you would have a classical, let's say, CFL, parabolic CFL condition, of course. The thing is that, in any case, for full implicit, semi-implicit, or full explicit scheme, the order of convergence is the same. It's 1/2 in delta t, meaning 1 in delta x, well, under the CFL condition or not, depending on whether you need it or not. And 1/2 is really due to the fact that you start with a discontinuous solution. You cannot hope for more than 1/2. It's not possible. So anyway, well, with a very simple condition, you can have you can use with the characteristic condition, you know that you should try the fully implicit scheme. So here are some numbers just to show you that, for example, the implicit in delta x, you can see that as you multiply by 2 the number of points, you divide the error by 2, so that's okay. And you can see that, of course, for the explicit scheme, it's for the same discretization, it's a bit more, it takes a bit less time to compute, but you have to invert a system. Okay, it's not a very difficult system since it's tri-diagonal and you can compute it in advance. Still, doing the computation is a bit more for the same discretization, for the implicit. But the thing is that, in any case, if you want to have something rather good, I mean, from the error point of view, the fully implicit takes a lot less time than the full explicit, for example. So it's in good agreement with what we thought at first. Okay. So now let's have a look at the moving interface in the case where the characteristic condition is over B. So according to what I showed you on the two-phase solutions, the interface should move to the left. So that's this case. Okay, what are M of tau and W of tau? In the previous case, the steady case, M of tau was actually exactly the Laplacian. It didn't have to change since the interface was steady and it was completely explicit. Thing is now, since the interface is moving, there is one point where we will have a problem when discretizing actually phi. So if you want to compute the finite difference for phi of u j plus 1 minus 2 phi of uj plus phi of u j minus 1, if they're all in the same phases, you have no problem. If they are in different phases, but the interface is not moving, you have no problem, because actually there is one term that's left, but the matrix is constant. But actually, if here phi of u, if uj, for example, happens to be in the unstable phase, then phi will change expression. And so it means that the matrix will change also. And that's the problem we actually encounter. So to model the problem, what we were having a look at the beginning was a model where the initial condition is just, you start with everybody in a stable phase, in the left-hand side stable phase here, in the right-hand side stable phase here, but on the boundary, on the interface here, you choose to be exactly, so you are, actually the solution is here, here, and here. Here is uj for j less than L. This is ul, and this is uj, j larger than L plus 1.
Can I ask you something?
Sure.
Just to understand. In this case, the theoretical result of the say Terracina and Massia that you said, does it give you uniqueness?
Yes.
In case that you have top jumping?
Yes. So numerically, since you have to discretize, it seems like a good idea to have a look at this model instead of having a look at the full model with the full let's say a full continuous problem, of some form. So thanks to a Taylor expansion, what you see in this case is that the matrix M of tau will be really the matrix of the Laplacian, times a diagonal matrix, which is very nasty. Well, diagonal matrix should be okay, right? Since what we know is that when you multiply by a positive diagonal matrix, it doesn't change the signature of the matrix. If you have A times D, where D is a diagonal matrix with positive terms, then the spectrum, actually they have the same number of positive, negative, and zero eigenvalues than A. But here, the problem is that this, seemingly sympathetic matrix is very nasty because it has one negative value, one negative component. And so, of course, it changes the spectrum of AD. The number of positive, negative, and zero eigenvalues is changed. The thing is that with a lot of computations, what you can show is that actually the signature of AD is really, so I'll show you after on the next slide, but I can give you a flavor of it. The spectrum of AD actually will be 0 since A has 0 as an eigenvalue, so that you cannot do anything about it. Then you have a negative eigenvalue, which is nasty, more or less, and the rest of the eigenvalues, so let's say mu1 to mu j minus 2, are positive. So these ones are okay, actually. This one is okay because we had the same one in the steady case. And mu minus 1 doesn't seem okay. Thing is that it is absolutely necessary to have this eigenvalue, because what it does is that it helps the scheme actually to push the middle point that will cross the unstable phase, because of course a fully explicit scheme has no idea, has no a priori ideas about two-phase solutions. It doesn't care about two-phase solutions. So the thing is that since the interface will be moving, there is a point that will change phases, and it will not jump, since actually it's the fully explicit scheme is a fairly continuous thing. So, well, it needs a mechanism to have this point cross completely the unstable phase to go from left to right. So that's what we can see here. So this is the Taylor expansion. It gives you that, actually. The Taylor expansion explains how to choose what the matrix M of tau will be, by telling you that if you have a look at so this is the discretization. You have a point here, 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 here. So actually this point will go down, this point will go down, this point will actually increase, this one will go down. And that gives you exactly the form of the matrix I gave you. So actually you can try and have an approximate exit time for this point, which will cross the unstable phase. So let's say the unstable phase is within these two values, actually. So this point will cross completely this region, and you have, since actually you can show that this matrix B has only simple eigenvalues. So you can compute explicitly, more or less, the spectral projectors. And so you have exactly, you know when the point will exit the unstable region. The only problem, of course, is that it's approximate, so you cannot use it for a scheme. So you cannot use, the conclusion is that you cannot use a fully implicit scheme in this case, because the fully implicit scheme needs to, you need to invert some matrix, and the problem is that you don't know in advance when the matrix will change, and so it's not reasonable. So here is what we obtained using the fully explicit scheme. Sorry. Here you see that this point, actually 2 points have already crossed the transition, the unstable phase, and the thing is that you can show that there is only 1 point at a time that crosses the unstable region, meaning that the interface is really localized. Okay. This is only actually a close-up of this region, just to show you okay. So here is the numerical, actually the numerical simulation we obtained. It corresponds to the U phi of u scheme I made around here. And here you see that, of course, this is not something you can admit from the two-phase solution point of view. This should not exist, of course, this point. So this is the interface, the numerical interface you actually you compute from the explicit scheme. Problem is, of course, you have some oscillations because with the numerical problems, it's difficult to identify exactly where the transition is. However, you can recognize, of course, the parabolic shape of the interface. So that's okay. So just in 2 minutes, I'll explain you how we actually introduced a two-phase scheme, which actually forbids any point to be in the unstable region. What we do is that we use this this intermediate value phi of u. So the key thing is to use the value 1/2 of f of u of psi t minus plus phi of u of psi t plus it actually is reproducing the Riemann problem at a very, very small scale. Then, using this this new value, either if it's within AB, we keep it as it is, since we know how to. Well, the scheme knows how to deal with this. If it's not within AB, we truncate it to put it to A or B. And so, with this procedure, actually, we isolate the 2 points around the interface, and we impose these values, meaning that we solve the diffusion equation on the left and on the right, and then we recombine the values to have the connection between the two phases. So in the end, you have this kind of algorithm that I don't want to detail. There is a CFL condition, of course, since it's a fully explicit scheme, you cannot hope for a miracle. So it's a parabolic condition, but there are no points in the unstable phase, and it's fairly easy to generalize to the cubic case. So here is the relative error. So it's percentage. So it's very, very small. It's the relative error of the position of the interface with respect to the exact solution, the explicit solution I gave you of the Riemann problem. So you see that there are a lot of oscillations for the fully explicit scheme, and for the two-phase scheme, actually, it's much, much more accurate. Okay, so. Sorry, so the next thing we'd like to work on would be the real cubic diffusion equation, which was introduced by Jekyll and Frisch. Of course, we'd like to go to higher dimensions, but that means we have to find other adapted methods, because here everything was 1D, so finite differences in 1D is almost the same as anything else in 1D. Of course, going to 2D or even 3D is much more intricate. Okay, thank you for your attention.